Good evening and welcome to the problem solving session. Of course, microwave engineering. So, today we will have our session 11 based on the content of week 11, uh, which the topic of coverage in week 11 is microwave integrated circuits. Just Can you please confirm if I am audible? Hello. Okay, thank you. So let me start with the different topics covered in the week 11. One is the planar transmission lines for microwave integrated circuits. So, as you have gone through the video lectures, you might have come across the different types of transmission lines. Can you please tell me some of them, the different types of transmission lines which you have come across in the video lectures? I can give you an example. One is strip line. Any other examples? Yes, you have microstrip line. Yes, as you rightly said. And also you have, yes, exactly, the coplanar waveguide. Coplanar waveguide. And there is also something called a slotted line. Okay. So all these are different types of planar transmission lines. To quote some of them, the one of the very commonly used microstrip line. So here, so this is a side view. Please don't confuse. This is side view of this cross section. So this is a conducting plane, which is the basically the microstrip, and this is again a conducting plate, which is nothing but a ground. Okay, so this is the microstrip and this is the ground plane. As you see, the width of this is called as the width of the strip. So you can see that it's like two plates separated by a dielectric, but one of them has a smaller width. So this is a microstrip line, and what is the kind of propagation of wave? So you are familiar with the TEM, the transverse electromagnetic wave propagation. Can you say, is it a TEM mode of propagation here in the microstrip line? So if you just look at this, so you have two plates. I mean, there are two conductors. So there will be field between these two. Okay, there will be field like going on like this, and also there are some fields which emerge like this. Okay, so we can say that this is not really purely TEM. This can be called as quasi TEM mode of propagation. Okay, so this is the mode of propagation in a microstrip line, whereas in strip line you have the dominant mode of propagation as TEM. It's purely TEM. And how about the to just to explain the structure of a coplanar waveguide and where it will be to understand the need or where it will be useful. So here, as you see in microstrip, so the upper plate is a conductor. Again, a down bottom plate is also a conductor. Between, so these two are separated by a dielectric. Okay. Whereas in a coplanar waveguide structure, you have structures like this. Okay. So this, say if this is the strip line, okay, or if this is the main conductor, this will be the ground. Okay, so the advantage of having these, what is the advantage of having this coplanar structures? Any idea why this is beneficial? Okay, reduce the low radiation loss. That is one thing.
Madam, madam,
Yes, yes, please go ahead.
for microstrip line, bottom is ground, madam. Top is strip line positive.
Yes,
For CPW, both positive and ground are on top of the dielectric means we have to reduce the loss,
yes,
power
yes.
losses from radiation.
Okay, okay. So that is one of the advantage. And if you imagine, say, if you want to, say, in case of microwave integrated circuits, maybe you require some shunt or series lumped elements. So when I say lumped elements, I would say lumped resistor or like inductance or capacitance. Okay. So suppose if you want to mount any kind of shunt or series lumped components, which one will you prefer? Will it be a coplanar structure or will it be a microstrip structure? Is there any advantage of having a coplanar structure? So as you see, so if I want to mount something in shunt, for example, in shunt between the conducting plate and the ground, which would be a preferable one? Is it the same plane or is it the two different plane will be convenient?
Madam, for microstrip line, the capacitance is more if you are increasing dielectric. Here, the capacitance is less, madam. Why? Because positive and the ground plane, the width is very, very minimum for coplanar. So, we have to
Hmm.
reduce the capacitance value.
Ah, okay, okay, okay. That is one other aspect. So, what I want to say is, say for example, if you want to mount a shunt element, okay. So suppose you have something like this. So this is a two line transmission line. You have something like a capacitance which is coming in parallel. Okay, so this is the main conductor and this is the ground. So between conductor and ground, I want to mount a capacitor. Assume that you want to mount a capacitor. So which will be convenient? Is it a coplanar structure convenient or a microstrip structure? For example, in a capacitor structure, if you want, yes, yes, that is right statement. It is a coplanar waveguide structure. So it will be easy to just mount it here. Okay. So just since both the conductor and the ground plane are in the same uh, since both of them are in the same plane, it's easier to mount the lumped elements such as inductors or capacitors, especially the shunt elements. Okay, so that is one aspect. Okay, the other thing was which was covered in week 11 was the lumped elements for microwave integrated circuits. So as I mentioned right now, what are the lumped elements? This is resistance, inductance, and capacitance. So, how do we realize such elements in a microwave integrated circuits? So, we will have some questions on this. And towards the end of the week, I think you had video lectures on MMIC and HMIC. So, basically, MMIC is monolithic microwave integrated circuits and HMIC is hybrid microwave integrated circuits. So both different types of microwave integrated circuits. We'll come to them as and when the questions come. First, I would like to start with a few things. Uh, a few questions. Okay, let me just start with some of the questions from. So we'll start with this topic first. that is MMIC and HMIC. Okay. So the first question goes like this. These are MCQs. Please do respond in the chat. Substrate of an MMIC must be what? To accommodate the fabrication of all the type of devices. So we are talking about a monolithic microwave integrated circuit. So what kind of substrate we should have? Is it a semiconductor? Is it a insulator? Is it partial conductors? Is it metals operable at high frequencies? Please do respond in the chat. What do you think? Yes, they are basically semiconductors. Okay, the substrate should be a semiconductor to accommodate the fabrication of all type of devices. So when I say all type of devices, so it could be an active device, it could be anything. So, and the other thing is, so which semiconductor to use? Okay, so that will depend on the frequency range. That will depend on the frequency range. Say which material, which substrate material you require. So based on the material properties such as especially the relative permittivity, will based on that we'll choose the material. So we need to look at what frequencies we need to operate. Based on that we choose the material and where whatever is the semiconductor material. Can you give any example of such a semiconductor? Which is commonly used. So one of the commonly used this thing is gallium arsenide. There are a lot of substrate materials. I just gave one example of that. Okay, let's move to the next question. Transmission lines and other conductors in microwave devices. So basically this means the integrated circuits are usually made with. So is it a gold metallization, silver metallization, or a copper metallization, or a zinc metallization? So you understand that you want to draw some conductor lines. Is it with a gold or silver or copper or zinc? Okay, so the answer is gold metallization. So, so whenever this gold, so I just wanted to give some extra point. I wanted to add some point to this. So there is a substrate and you want to make some conductor lines. So the gold has to be what you call gold has to be deposited. So to improve the deposition, I mean, if you have a substrate and if you want to improve the adhesion of this gold material to this substrate, a thin layer of chromium or titanium will be deposited first. Okay, a thin layer of either chromium or titanium, such that this adhesion of gold to the substrate is improved. Okay, and also you know that what is the speciality of this chromium? These are relatively lossy material. So either whether it is chromium or titanium, they are relatively less lossy. They are relatively lossy metals. So we have a thin layer of such metals just to improve the adhesion of gold to the substrate. Okay, moving on to another question. Okay, let's go. Yeah, is there a question?
Hello, madam. Hello, madam.
I think your voice is breaking. You can ask your doubt. Yeah, please go ahead. Hello. Okay, maybe if there is an issue with the okay, I think you are typing in the chat. For gold, increase the cost. Yeah, there is issue with the cost in case of gold. Yes, I understand. So yeah, so with when we talk about metallization, the most desirable one is gold. So um, we can also have other metallization for conductors. There are several options, either silver or it could be. So the most desirable one is gold, and it depends on the application, especially if you can't compromise the in a particular application, if you can't compromise the conductivity of this part, then we go for gold. Or if it could be compromised to some extent, depending on that, the material will be having some changes. Say for example, if you want a mirror or something, then those kind of there could be gold mirrors which will have the maximum reflectivity, and it could be silver. It will have some amount of reflectivity which is little less than the gold. Even aluminium is a possible option, but then there are, for different material, there will be some plus and minus. So depending on the application, and if we cannot make some compromises, then we go for the best options out there. Okay, moving on to the next question. To fabricate a low frequency circuit using the hybrid microwave IC methodology, the material width dash is preferred. Is it a high dielectric material, dielectric constant material, or is it a low dielectric constant material? Is it a high resistivity material or low resistivity material? For low frequency circuits, so please notice. So it depending on the I had mentioned a few minutes back, depending on the frequency range which we are operating, we choose the semiconductor, or we choose the material. So in case of low frequency circuits, I'm waiting for everyone to give your options. So, as you all said, at low frequency applications, a high dielectric constant is desirable because that will result in a smaller circuit size. Whereas at high frequencies, the substrate thickness must be decreased to prevent the radiation loss and the other spurious effects. Going on to the next question. For the capacitors used in MMIC, so MMIC, you know that it is monolithic microwave integrated circuits, the insulating dielectric films. So, in case of what kind of dielectric will be used as while realizing the capacitors? That's the question. So you know that a capacitor has a dielectric in between. So what kind of materials will be used as a dielectric film? So basically, when we talk about in terms of fabrication or integrated circuit technology, there we say the thin film coating. It's not a dielectric material. We say the thin film coating will act as a dielectric. That's the reason it is called as film, insulating dielectric film. So, what is that option? Do you think? So remember, it should be a insulator and a dielectric film. And a dielectric. It should be an insulating material. That's the key point here, which is very clear. So the answer is silicon oxide. So different oxides of silicon is generally desirable to be the dielectric film, insulating dielectric film in case of realizing capacitors uh, in the monolithic microwave integrated circuits. And it can also be, there are other options, silicon dioxide, and there is another option of silicon nitride and titanium oxide. There are several options. It depends, again, depends on the dielectric constant. Basically, these materials have high dielectric constant and also low loss. And generally compatible. So these are materials compatible with the MMIC circuit design, MMIC circuit technology. So I have one question. Is there a drawback? So I don't have the question right here. Is there a drawback with the monolithic microwave integrated circuits? This is a general question. You can comment on this. Excuse me. What is the drawback of monolithic microwave integrated circuits? So basically, I told in the beginning, this monolithic microwave integrated circuits are generally on the substrate, basically a semiconductor, and all the components are being integrated on the substrate. So what happens here is they tend to waste large area of this expensive semiconductor substrate for components such as transmission lines and hybrids. Okay. That is one of the major disadvantage or drawback with the monolithic microwave integrated circuits. But whereas if we think of circuit flexibility, okay, so suppose if you want to, so if we have, so the fabrication, if you want to fabricate something in an MMIC, that is much easier. We have the circuit flexibility and the performance can be enhanced and require, we don't have to fabricate the entire device. So it can be fabricated on the substrate material. So with respect to circuit flexibility, this MMIC is a better option. Whereas one disadvantage with this is it tend to waste large area of the semiconductor substrate, especially in realizing transmission lines.
Madam?
Yes.
Hello?
Hello.
Madam, what is the difference between material and compounds, madam?
Compounds, did I mention anywhere? Or so what I am trying to say here is, so you, for monolithic microwave integrated circuit, you need a material. So that would be a semiconductor material, a semiconductor substrate. So compounds, did I mention anywhere? I don't know.
No, madam. Last assignment 10, ferrites are ferromagnetic components is there. About ferromagnetic, that questions, madam. I put it true, but it came false. I thought material compounds are same.
Okay, okay. So you are talking about that question,
Assignment.
assignment question. Okay, okay,
Yes, ma'am.
okay. Just let me go back and see. Mm. Just a moment. I'll see the question once.
Okay, ma'am.
So the question of assignment 10, that is about first question is ferrites are ferromagnetic material. So ferrites are not ferromagnetic material, they are ferrimagnetic, right? Is that the question you are mentioning or is it a different question? So the
Questions only, madam. But
okay, so here there is mention of ferromagnetic and ferrimagnetic. So I hope you understand the difference of ferromagnetic and ferrimagnetic. So ferrite is a ferrimagnetic
okay,
material.
ma'am.
So that is so it is dependent on so the true or false is based on that. So you know that ferrite is like a ceramic
Okay, madam.
material. So it is that it's so very magnetic in the sense they are being attracted by the magnetic field, or we can say that it can be magnetized. So ferrites are very magnetic, which can be magnetized with the application of some field. That is the point there. Okay. Okay. Thank you for pointing out this question. Yeah. Okay.
Okay.
So we'll move to. Okay, I have a few questions, numericals. Uh, I request everyone to try uh, with me and give the options. So here, you have an inductance, say 5 nanohenry. If an inductance of 5 nanohenry is 10% higher than its nominal value. Okay, so effective inductance, we can say that it's 10% higher. So how do we write it? 5 nanohenry plus 10% of that. So 5 into 10 by 100. Okay, so I can say 5.5 nanohenry. Okay. So the effective inductance is 5% higher, okay, than the nominal value at a frequency of 2 by pi. So the frequency is 2 by pi gigahertz. Neglecting the series resistance. So always remember when we say a inductor, this leads of the inductor will have a resistance, which we call it as a series resistance. So if we are to neglect that series resistance, what is the value of parasitic capacitance? So the idea here is you have this kind of a circuit L and CP. So in video lectures, you have come across this, and the effective inductance is L divided by 1 minus omega by omega p the whole square, where omega is the operating frequency and omega p is 1 by root of LCP. That's a resonance frequency. So from this, what do we need to calculate is the parasitic capacitance, that is CP. Okay, can we calculate that? So here we know LE, we know L, and we also know the operating frequency. Can we not find the omega p? So now I request everyone to please find out omega p.
Madam, I have a doubt, madam.
Okay.
Hello?
Yes.
Madam?
Yes, please.
Madam, in a rectangle waveguide that assignments for operating frequency is 30% above the cutoff frequency, madam.
Okay.
That statement will put a f naught which is equal to 100 plus 30 by 100 into fc.
Yes.
But here you are putting madam 5 plus 5 into 10 by 100. That statement I cannot madam. How you are putting like that 5 plus 5?
Uh,
100.
okay. I'm not remembering the question exactly. So I think it was something like this. So 30% higher than.
Yes, madam. The statement is like this only, madam. Instead of inductor frequency, madam, operating frequency which is equal to 30% above the cutoff frequency.
Okay.
That's what, madam. There
Ah,
they put 100 plus 30 by 100.
so
That's what, madam.
here you have FC into 1 plus 30 by 100, right? I think that was something which I mentioned in that question. So we can write 130 by 100 FC. Something like this, right?
Yes, ma'am.
1.3 FC. So this
Yes,
also
ma'am.
same thing. 5 into 1 plus 10 by 100.
Okay.
Okay. Okay. So yeah, now by substituting this, so effective is 5.5 nanohenry and this is 5 nanohenry divided by root of 1 minus omega is 2 by pi. So this is frequency. So do calculate omega is 2 pi f, 2 pi into 2 by pi. So that will be 4 into 10 power 9. So this will be 4 into 10 power 9 by omega p the whole square. Can you now find out omega p? What do you get as omega p? Okay, you are saying the final answer. Omega p. I am asking the omega p. Okay, so omega p is 13.33 into 10 power 9. And if you equate that to 1 by root LCP, so this will be 1 by root of Ls. Again, the actual the inductance value is 5 into 10 power minus 9 into Cp is equal to 13.33 into 10 power 9. From this, you can evaluate the value of Cp. Answers for Cp, if you have tried, I request everyone to try so that you can clarify if at all you have any doubts. Yes, right option would be 1.14. Yeah. So it's closer, the option closer to option B. So actual value will be 1.125 picofarad, closer to option B. I hope this is clear. So this is a case when inductance in parallel with the capacitance. So the next question which I have is something similar, but capacitance in series with the inductance. So this is C and this is Ls. Okay, here the nominal value of capacitor is 20 picofarad and the parasitic inductance. So this is C C is 20 picofarad. LS or LS, let me write it as LS. LS is 0.2 nanohenry. The question is, what is the value of capacitor at a particular frequency 1 by pi? So you know that based on the frequency, the value of capacitance will change. So the question is on, at this frequency 1 by pi gigahertz, what is the uh, so omega is 2 pi into 1 by pi, which is 2 into 10 power 9. And you know that CE is C by uh, 1 minus omega by omega is the whole square. You know the value of C, you know the value of omega, and there is something which we need to find, which is omega S. Omega S is 1 by root of Ls into C. So 1 by root of Ls is 0.2 into 10 power minus 9 into C is 20 picofarad. Okay. Any answers for omega S? Omega S. Please do calculate. And if you could type in the value what you get for omega S. What is the value of omega S? I'm waiting if you could find it. Just substitute Ls and C in this equation and try to find omega S. Omega S. Yes, omega S is what you said is right, 1.58 into 10 power 10. Maybe I can write it like this, 15.8 into 10 power 9. Okay. So with that, omega S, let's substitute here. The nominal value of capacitor is 20 picofarad divided by 1 minus omega by omega S. Omega is 2 into 10 power 9 divided by omega S is 15.8 into 10 power 9. So that's the reason I kept it as 10 power 9. So this gets cancelled. And any answers, final answers for the value of capacitor at the operating frequency 1 by pi gigahertz? Option C. Are you all getting the same? Option C. I request everyone to answer so that we'll be able to clear your doubts. Yes, thank you all for responding. So the right answer is 20.32 picofarad, which is close to option C. Okay. 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 Now, let's move on to another question, wherein this question has how do we realize a lumped element such as a resistor? Okay, how do we realize a resistor in a strip line? So, as you see the question here, 1 ohm planar resistor is to be made using a resistive material having a resistivity. So, the resistivity is 10 power minus 6 ohm per meter. Width of the strip used to make the resistor. So, width of the strip is 5 times the thickness. Okay, so a strip, if you consider a strip, there are two parameters associated with a strip. Always you have to remember this is, say, this is width and this is called as the thickness of that strip. Now, what is the question? If the length of the line is 20 micrometer, so you have the length of the strip line, okay, that is 20 micrometer. What is the thickness of the strip conductor? Okay, so we need to know only one thing. What is that? Resistance is rho L by A. That is a very fundamental equation. So, where rho is the resistivity, L is the length, and A is the area. Okay. So when I say realize a resistor with a strip line, what does it mean? I want a material. So that material has some rho, that is the resistivity. Now, and the strip line will have a length L. Okay, that is 20 micrometer. And what is the area? Area is always this multiply the width by the with the thickness. Okay, so that is giving you the area. So how do we do it? Let's try to realize a 1 ohm resistor. So 1 ohm is equal to 10 power minus 6 multiplied by length of the line is 20 micrometer divided by area is width into thickness. So width is 5 times the thickness, width into again thickness. Okay. So from this, so micrometer will replace it by 10 power minus 6. So 5 t square will be 20 into 10 power minus 12. So t square will be 4 into 10 power minus 12, whereas t will be 2 into 10 power minus 6, or I can write it as the thickness is 2 micrometers. So to realize this resistor on a strip line, okay, have the, so the thing is width is 5 times the thickness. So the strip line has a width which is 5 times the thickness with the and the length of that strip is 20 micrometer. Okay, for that we need a thickness of 2 micrometer. So what will be the width of the strip? 10 micrometer. So the final conclusion is width of 10 micrometer, thickness of 2 micrometer, and a length of 20 micrometer can realize a resistor of 1 ohm. Okay. So I hope you understand the concept of this question. So the answer option, as you all said, it is option D, 2 micrometer. Now coming to the next question. This is realizing a capacitor in a monolithic integrated circuit. So the value of capacitance, like before question, there was realizing a resistor. Now this in this question, you are going to realize a capacitor. And the value which you need to realize is 0.1 picofarad. And you have two capacitor plates, okay, and they are separated by zero point 0.1 micrometer. So this is the distance between the plates of the capacitor. And what is the material used as the dielectric? That is silicon. And in the question, so read the question. Uh, Capacitor in a monolithic integrated circuit has a capacitance of 0.1 picofarad. The capacitor plates are separated by 0.1 micrometer, and the dielectric constant of silicon used as dielectric material is 11.7. So epsilon r is 11.7. So that is the dielectric used between the two plates. Okay, so silicon is the dielectric. Now, suppose if the capacitor plates are square plates. So imagine you have two square plates. What do you mean by square plates? The sides are same. Okay. So what will be the area of the square plate? A square. Simple. Now, what is each side of the capacitor plate? So you are asked for the length of the capacitor plate or the side of the capacitor plate. So how do we realize it? Basically, what length should be the capacitor plate length? So to understand this, use the fundamental equation. Again, in resistor, we use the fundamental equation rho L by A. Similarly, look at capacitance such that you know epsilon 0, epsilon r, A by D. Okay. Epsilon r is the relative permittivity of the material used as the dielectric. A is the area of the plate, D is the separation, and C is the capacitance to be realized. So how do we do it? 0.1 picofarad is equal to epsilon 0 is known, 8.85 into 10 power minus 12. Epsilon r is 11.7 into area divided by the distance between the plates, 0.1 into 10 power minus 6. Can you give me some answers, any answers for the area of the plate? The question is about the side of the capacitor plate. Can you give the answer for area of the plate first? Hope you are trying. So, any answers for the area of the square plate used as a capacitor plate? Yes. Yeah. Thank you, everyone. You know that the simplification becomes much easier. So, as you rightly pointed out, yes, the answer is right. Say 9.65 into 10 power minus 11 meter square. Okay. Just watch out for the units. Just make sure that you are using the right unit. So then you should be getting this answer 9.65 into 10 power minus 11 meter square. Okay. From this, calculate the side of the plate. Nothing but root of area. So what will be the options, I mean, right option among this A, B, C, D. Uh, there is option, answer option right there. Can you check once again? Okay, right option is 9.82 micrometer. That is option A. So I hope this is clear. So, are there any doubts with respect to today's session or the previous week's assignments or sessions? Now, I the session is open for discussion. If you have any doubts, you can ask them. Or if you want me to repeat any of the questions, can you please let me know which is question number 8 of which assignment you are mentioning? Assignment 10. Okay. Okay. Suppose, okay. Let me just.
Hello, ma'am.
Hello.
Ma'am, in question number 8, assignment 10, we
Okay.
use we use the relationship delta phi is equal to 2 pi beta
Okay.
plus minus beta minus upon beta plus plus beta minus. And then if you put the delta phi is equal to pi by 2, then we cannot get the relation pi is equal to beta minus,
Yes, yes, yes. That is
because
true.
pi is equal to 4 pi beta minus. That's why answer should be false.
It should be false. Yeah, yeah. I am looking
Yes,
at that
yes.
question. Yeah, right, right.
But the solution is true.
Okay. Uh, yes. The Faraday rotation is minus, sorry, plus pi by 2. Pi by 2 is. Hello. So if you have noticed, there is a small thing here. I think my screen is visible. So, okay, I make it, my question is plus pi by 2, okay? So what do we get if it's plus pi by 2? The 2 gets cancelled and this becomes beta minus beta plus, okay? And we know if you take say ratio or something like that, let me start from here. So all of you agree till here, right? So I just substituted the phase value pi by 2, that is equal to beta minus beta plus. Okay, suppose I take beta minus outside, beta minus outside, then I will get 1 minus beta plus by beta minus. Okay, so beta plus by beta minus will be omega root epsilon into mu plus k by omega root epsilon into mu minus k. So omega root epsilon will cancel, or the ratio will be root of mu plus k by mu minus k. Okay, so beta minus into 1 minus root of mu plus k by mu minus k. Is this the option? Answer option is correct, right?
Why this one minus?
Still there is 1 minus. I am just looking at that. Beta minus into 1 minus. Okay, I think this is the right answer, but I suggest you all to go through this once again. I hope you understand that it can be written in terms of beta plus, in root of mu plus k and mu minus k. But then still there is some small error here. Uh, I suggest you please write in the discussion forum, because as I have mentioned before also, this assignment evaluation and correction has been taken care of other section or other session other set of TAs. So to get a quicker response, I suggest you to write in the discussion forum. Please do post with the your solution, okay, so that they look into that. I hope you are.
Minus is missed, madam.
Yeah, minus, there
You
is a
take
small
minus
there
common.
is a difference. So you can just type in the you can just take a photo of the solution and try to.
Already I posted in the madam. I posted
Okay,
ask
okay,
questions.
okay, fine. So then it will be taken care of, okay. Any other questions you have?
Madam,
Yes.
from assignment 4 to 9, solutions will be sent
Oh, okay. It's not updated. Okay, okay.
up to 3 only solutions we got it, madam.
Okay, okay. It will be updated in the NPTEL module. I mean, there won't be any emails. We won't be sending any emails out. So it will be soon be uploaded in the. Are there any questions from the previous week's assignment or this week's any queries you have?